Hello everyone, I am Bonilla Licea and I am going to present you our paper called Optimum Trajectory Planning for Multi-rotor UAV Relays with tilt and antenna orientation variations. This is a joint work with my colleagues Giuseppe Silano and Martin Saska from the Czech Technical University in Prague and with my colleague Mounir Gogo from the International University of Rabat. This work was partially funded by the European Commission Horizon 2020 program, the Aerial Core project, and the Czech Science Foundation. Before jumping into discussing the main core of the paper, let us consider quickly how quadrotors move. If the quadrotor has to hover, then the platform is horizontal, and this is obtained by making this propeller and this propeller produce the same thrust. If the UAV wants to go to the left, in this case, the right propeller has to produce a higher thrust than the left propeller in order to have the UAV platform tilt in this way, and then it moves towards the left. If the UAV wants to move towards the right, then this propeller has to produce a higher thrust, then the platform becomes tilt in this way and the UAV starts moving towards the right. Now, this is a key point for the paper that we are going to present. And the scenario considered in our paper is this. We have a UAV called UAV2, which is performing some task, for example, exploration. And it has to communicate with a base station. Now, we consider that direct communication is not possible, maybe because of the distance between both nodes or some other considerations. So we introduce a second UAV called UAV1, which will act as a communication relay between the UAV2, the UAV, and the base station. So we have the link UAV2, UAV1, UAV1 base station. Here in blue, we see the wave being transmitted from the UAV2 to the UAV1. And here in red, what we see is the angle of departure of the wave radiated by the UAV2 and the angle of arrival from received by the UAV1. Now, as mentioned before, as the UAV moves, it has to tilt. And as the UAV tilts, these angles, the angle of arrivals, the angle of departures will be changing. So that means that if we consider the antenna radiation patterns, the total channel gain will depend not only on the distance between the UAVs, but also on their individual tilt, which will be changing as they are following their trajectory. So this is important because the channel gain will depend not only on the distance, but also on the tilt of the UAVs. As we said before, we're considering how the UAVs tilt as they move. In order to do that, we have to consider the dynamics of how the UAVs are moving. In order to do this, we're restricting the motion of the UAVs according to these splines. You can see more details into the paper. We are also considering that each UAV is equipped with a half-wave antenna dipole, and then it is located, for example, for the UAV1, the antenna is located in the center of mass and aligned according to this vector. The same happens for the UAV2. So in this case, this is again the wave radiated by the UAV2, and then the angle of arrival is measured in this way, and the angle of departure of the wave radiated by the UAV1, which arrives to the base station, is this angle. This is the angle of departure. As we are considering a half-wave dipole antenna, this is the antenna radiation pattern, okay? Now, regarding the channel model, we are considering line of sight between the UAV1 and the UAV2, as well as between the UAV1 and the base station. we are neglecting the small scale fading. We are also considering that the base station has some beamforming that it's always pointing towards the UAV1, and so we disregard the antenna radiation pattern of the base station. We assume that it is constant. So this is the channel model that we are considering, which is an additive white Gaussian noise, considering just only the antenna radiation patterns of the receiving and the transmitting antenna. Now, mathematically, this is the problem that we are considering in the paper. So we are considering that the UAV2 is following a certain trajectory, which is known by us, and we have to devise the UAV1 trajectory by respecting first its dynamic constraints, considering how the UAV1, as it moves, it tilts. And considering all this, we devise the trajectory so that we maximize the amount of data transmitted from the UAV1, from the UAV2, towards the base station via the UAV1, which is acting as a relay. Mathematically speaking, this can be put in this form. This is the channel gain of the communications relay channel between the UAV2 and the base station via the UAV1 acting as a relay. Okay, this is the SNR of the UAV1 to base station relay. This is the SNR of the UAV2 to UAV1 link. Okay, here we are limiting the speed and the acceleration of the UAV1, and this equation is telling us, is providing us the splines that will be acting as a dynamical model for the UAV1 in order to consider realistic movements, which will provide us in how tell us how the UAV1 will be tilted during its whole trajectory, which in turn will affect the antenna radiation patterns here. Now, this is the cost function that we are considering. This is the cost function that we are considering. This is a maximizing problem, but first we transform it into a standard minimization problem. So we do some manipulations. Then we approximate this max function by a soft derivatable function. This is done by considering the definition of the edge infinity norm and the definition of the HP norm. See the paper for more details. So we end with this optimization problem. The restrictions are basically the same, but we now have a derivable cost function and a minimization problem. The antenna channel gains, we have some approximations which are simpler to consider in the optimization problem. Now, this optimization problem can be solved numerically using the Casadi library and the NLP problem solver. We consider for the UAV2 trajectory T2, which is taken from a previous paper of ours, in which the UAV2 had to do some inspection for a power tower. And this trajectory is realistic since it was already experimentally validated. Now, in order to test our technique, what we're going to do is, first, we optimize the trajectory of the UAV1 as we just presented with the technique proposed in this paper. And then we optimize again the trajectory of the UAV1, but disregarding the effects of the antenna. This means that now the channel gains do not depend on the tilt of the UAV. So this is done for the optimization model, but both of these trajectories will be tested with a realistic channel model in which indeed the channel gain will depend on the tilt of the UAVs. The trajectory duration of the UAV2 is 18 seconds, okay? And these are the results. In blue, we can see the trajectory of the UAV2. Here in this square blue is the base station, and this is the initial position of the UAV2. And here in green is the initial position of the UAV1, which will be acting as a relay, and its trajectory is marked in red. This is the first case that we discussed, in which the optimization trajectory of the relay is optimized according to our technique. And in this case, we have the trajectory of the relay optimized disregarding the antenna variations. As we see, by considering the antenna variations, the trajectory of the relay is totally different. In this case, if we disregard totally the antenna dependency on the tilt, the UAV1 trajectory is simply a scaled version of the UAV trajectory. On the other hand, when we consider the UAV2, the dependency of the channel gain on the antenna radiation patterns, which in turn depends on the tilt of the UAVs, we have a totally different trajectory in which the UAV2 tries to align itself with the antenna of the UAV2. Here we observe the normalized bit rates for both links, okay, in the first case scenario of our technique, and this is the result of the second trajectory, in which we are disregarding the antenna dependency on the tilt. As we can see, if we consider the antenna variations, the minimum channel bit rate that we obtain is higher than in this case, and also the total amount of data transmitted in this case becomes higher. In this case, the total amount of data is higher by 6%, and the minimum bit rate obtained is 17% higher than in this case. So by considering the antenna variations of the channel gain, which depend on the tilt, we can obtain a higher performance. So we have presented a framework in which we can design and optimize a trajectory for UAV multi-rotor relays by considering the effect of their tilt on the antenna radiation patterns, which will modify in turn the channel gain. Thank you for your attention.